AP Calculus AV, Unit 8, Day 8, Office Hours. This is the book assignment. There were 2 even problems. I'll do the last even one as part of the video. And here's number 12 answer. You can check that real quick. The rest should have been checked in the back of the book. So pause the video if you need to check that. A lot of these problems were just sort of like looking at pictures, and I'm going to redraw some of them here, which might have been a good idea for you also. The graphs of 3 position functions are shown in the accompanying figure. In each case, determine the signs of velocity and acceleration, then determine whether the particle is speeding up or slowing down. So A, picture looks like this. They're pretty simple pictures. It looks like that. And this is a position versus time curve. So, velocity, the signs of velocity and acceleration. So, velocity is the slope of this. So, since the slope is positive, then that means the velocity is positive. Since it's concave down, that means the second derivative is negative, which is acceleration is negative. And then speeding up, we explained in the notes, speeding up means acceleration and velocity are acting together in the same direction to speed you up. Doesn't matter which direction, but as long as they're in the same direction. They got to have the same sign. This one's positive, this one's negative. So it is slowing down. They're acting against each other. So the result is that particles going to slow down. B, same questions, different graph. Graph looks like this. So we're going to say, well, the slope is positive, right? So that means the velocity is positive. It is concave up. So that means the acceleration is positive. And since they're both acting in the same direction, the particle is speeding up. C, third graph. So this is just trying to ask you the basics of these. Another position curve looks like this. So the slope is negative on that graph. So that means the velocity is going to be negative. It's concave up. So that means the acceleration is positive, and since they're acting in different directions, the particle is slowing down. So that's that. That's number 1, ABC. Number 3, it says position function particle moving on horizontal x-axis is shown in the graph. So we could draw that graph real quick. So the graph kind of looks like that. There's a time 1, and then there's a time 0. Graph keeps going. Okay. So A says, is the particle moving left or right at time 0? Well, the slope of the curve is negative, so it is moving to the left. So negative slope gives you negative velocity, which means that particle is moving to the left. B, is acceleration positive or negative at time sub-0? So it is concave down. So that means acceleration is negative. C, is particle speeding up or slowing down? Well, we just looked. It has negative velocity and negative acceleration. So it is speeding up. Acceleration and velocity are acting in the same direction, speeding up in the negative direction. D, is particle speeding up or slowing down at time 1? Well, time 1, it has a negative slope, positive acceleration. So negative velocity, concave up, positive acceleration, opposite directions, slowing down. So there you go. Just kind of getting the basics of these ideas without having to do any major calculations yet. 5 says sketch a reasonable graph of S versus T for a mass that is trapped in a narrow quarter S-axis with positive direction to the right and scurries back and forth as follows. So it's just going back and forth in a quarter straight. It runs right for constant speed. So this is kind of like we've done this in previous tests where I give you like a car is on a trip, and so this is kind of like that. So it says it runs in a constant speed of 1.2 meters per second, then gradually slows down to 0.6 meters per second. So 1.2 would be a little more than a slope of 1, right? And then it gradually slows down to 0.6, which is like half that slope. It doesn't say it stops. Then it says, then quickly speeds up to 2.0, so that's going to be even steeper than that. Then gradually slows to a stop, so that's going to have a flat slope. But immediately reverses direction and quickly speeds up to 1.2. So reverses direction. So something like that. So that's number 5. Number 7 says the accompanying figure shows the graph of velocity versus time for a particle moving along a coordinate line. Make a rough sketch of the graphs of speed versus time and acceleration versus time. So they give you on number 7 a graph. I think there's actual values here. It gets up to 15, and it's velocity. And then time 0, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Okay, and so the original graph looks kind of like I think it has some dots here. Kind of looks like that. So it's kind of what the graph is. So that's the speed graph. So they want, no, that's the velocity graph. It says make a rough sketch of the speed versus time graph. Well, the speed is the absolute value of velocity. So it's going to be the same graph, but like as if it had an absolute value around it. So the positive parts are going to look the same. But then where it went negative, it's going to get flipped up. So the positive part stays the same, and then the negative part gets flipped up. That's what an absolute value does to a graph, right? Makes the negative parts positive. So this is like that's the speed graph, which is the absolute value of velocity. And then it says acceleration graph. Well, acceleration is the derivative of velocity. So essentially we're trying to sketch the derivative graph. So I would find any zero slopes, and those are going to be x-intercepts on, let's see, I think that one's there, right? And then these are all going to be positive slopes. It's like close to 0 here. I mean, it looks almost 0 here and almost like 0 over here. This is where it's the steepest up. We could estimate, I don't know, it's about, up Up. This is like 7. It's like up 8/1, so maybe like a slope of 8. That'd be the highest point. And here it's a slope down, and that seems kind of steep. That might be somewhere around here. Is supposed to be a rough sketch. And then here's another. That's where it's the most steep up, so that's going to be a peak on the acceleration curve. So I think it's going to look like this. It's positive acceleration to there, and then it goes back down to 0 here, and now it's negative acceleration from here. That's this point, and then back to here at 0, and it's a positive slope of velocity, so it's positive acceleration, and then it kind of goes back down to 0. So something kind of like that, close to that. Trying to guess a derivative graph, essentially. Okay, 9 says the company figure shows the velocity versus time graph or a test run of Classic Grand Prix GTP. Using this graph, estimate A, the acceleration at 60 miles per hour in units of feet per second squared, the time at which the maximum acceleration occurs. So they give you some pictures here, and you're going to be trying to estimate things from this. I mean, the numbers you get could be a little different. But it says we have a velocity versus time. I don't know if there was a position also. So here's velocity, which is miles per hour. And 5, 10, 15, 20, 25. This is time. 20, 40, 60, 80, 100. In the graph, I don't know, kind of looks like I was just trying to estimate some dots here. It's up to 100 at somewhere around here. So something like this. It's kind of what the graph looks like. If you're on graph paper, it'd probably be easier to make it look nice. So they're saying estimate the acceleration when it's at 60 miles an hour. So here's 60 miles an hour. What's the acceleration? Well, acceleration would be the slope of this graph. So you could draw a line and try and get a couple good dots and estimate it. So I estimated it was like, well, like here's a nice dot, and like here's a nice dot, and what's the rise over run here? And I said, well, run's 5. The rise is like from 40 to 45 to 75 or something like that. So that's like up 30 over 5. So I said for part A, the acceleration is approximately up 30 over 5. So 6 miles per hour squared. But the time is in seconds. And this, okay, so at first it is, it's miles per hour per second. So if we want to get it into terms of, I don't know. If you want to get in terms of, feet per second squared. Oh, geez. So we would have to convert this to, miles to feet. So there's 5280 feet in a mile. So that would get rid of the miles and change the feet. And then we have hours per second. So we need to change these hours. So we have over hours over seconds. So we got to change these to be 60 seconds over 1 hour. So it's going to be 6 times 5280 over 60, which would be like 5.280 feet per second squared. Something close to that. But that's the work. Okay, part B says the time at which the maximum acceleration occurs. Maximum acceleration would be the steepest part of the curve, which I think is like right at the beginning. So I'm going to say that the max acceleration, essentially you're doing EVT, check-in points, and critical points. So critical points would be anywhere where the slope of this was zero undefined, which is not. So then it's really going to be the endpoints that you got to check. Max acceleration is at time t equals 0 seconds. Should be using units. Anyways, kind of interesting. Okay, 11 says, 11 we actually get to do some work for 11 and 12. We're doing the same thing. It says the position function of the particle moving along the coordinate line is given, where s is in feet and t is in seconds. Find the velocity and acceleration functions. A, find the position, velocity, speed, acceleration, and time t equals 1. C, at what times does the particle stop? D, when is the particle speeding up, slowing down? E, find the total distance traveled by the particle from time t equals 0 to time t equals 5, which is something we haven't talked about. So I'll show you how to do that, but it's something we're going to go into more detail about soon. So they give you the function, and of course tell you that time can't be negative, which probably should just assume. So A, we want the velocity and acceleration function. So velocity is just the derivative of this, 3t squared minus 12t, and acceleration is derivative of that, which is 6t minus 12. So that's pretty easy. B, it says find position, velocity, speed, acceleration, time 1. So we just plug 1 in to each of these equations. So we can get -5. I don't think, do we have units here? Oh, feet and seconds. So that's going to be feet equals position at 1. And then velocity and then speed. And velocity is going to be feet per second. We should be using these units. So that's velocity at 1. The speed at time 1 is just the absolute value of velocity. So that's just going to be 9 feet per second positive. And then the acceleration at time 1. And acceleration is going to be feet per second, or feet per second squared. So there we go. All right, that's B. C says, what time does the particle stop? So that's when velocity equals 0. So our velocity equation is 3t squared minus 12t, and we're going to say equal to 0. And so we're going to factor out a 3t. So we're going to say it stopped at, did I make a mistake? Let's see, 4 seconds. Let's put the units. D says, when is the particle speeding up, slowing down? So the best way to do this is line checks of velocity and acceleration. It depends on the sign of velocity and acceleration relative to each other. So we put the velocity 0 and 4 on there. Test the time, t equals 5, positive, negative, positive. And then we're going to do acceleration right below it, try and line it up. Now we got to find when acceleration equals 0. So that's factor it. 2 should be right here. And then we test a value, different value. Make sure you label your line checks. T equals 3, positive, negative. So speeding up is when they have the same sign. Speeding up for when they have the same sign but positive, 0 to 2, and t is greater than 4. We could do interval notation if you want. Slowing down for 2 to 4 seconds. Now, as far as like including the endpoints, I guess we usually include the endpoints for velocity but not acceleration. So like at 0, we would include velocity, and we'd also include acceleration because it's in the middle of acceleration. At 2, we wouldn't include because it's the endpoint of acceleration. 4, we wouldn't include because it's the endpoint of acceleration. Slowing down, they have the same sign. I wouldn't include 2. Well, let's see, 4 we would include it. And then we include 4 here because 4 is the edge of velocity. So now E is something that we haven't really talked about. It says find the total distance traveled. And I'll show you a shortcut for that, and we'll explain it in upcoming notes. Its position, you got to put the endpoints on here. They told you 0 to 5, so they just told you the endpoints, and then any turning points where the velocity is 0, put in there. Calculate the position. So you plug these into the original equation, you get 0. If you plug 4 in to S, you get 64. What do you get? 4 times 4 is 16. 2 is 4. 64 minus 6 times 16 is 96. So that's negative 32. Then you plug 5 in, you get 125 minus 150, so that's negative 25. And if you find the distance between these, distance is always positive, absolute value of the difference, and you add those up, you get the total distance traveled by a particle. So total distance is 39. The units are feet. So that's how you do total distance. Okay. Another problem like that, an even on 12. So 12, they give you the position function. And then A is supposed to find velocity and acceleration. So velocity is derivative of this. So that's going to be 4t cubed minus 4. And acceleration is going to be 12t squared. So that's part A. Part B, you want to find position at time 1. So you plug time 1 in. Get negative 3, you get negative 1. Units are feet. And then velocity at time 1. That's feet per second. And then speed at time 1 is just the absolute value of velocity, so 0 feet per second. And then acceleration at time 1, and so that's going to be 12 times 1 squared, so it's going to be 12 feet per second squared. That's acceleration at time 1. And then C was wanting to know when the velocity is 0, when the particle is stopped. So we're going to take the velocity equation and set it equal to 0. So we're going to factor it. Cube root of both sides, no plus or minus, is an odd root. So t equals 1 second. And then d is supposed to find when speed up or slowing down. So we're going to use that information to help us. So we're going to do a velocity line check. Test a point. Label your line check. Tell me what you're testing. T equals 2. It's going to be positive, negative. And then we need to do acceleration line check. So acceleration is 12t squared equals 0. T equals 0. So line it up relatively correct. Test a point. T equals 1. Positive. Stays positive. right? It bounces off the graph. So speeding up is when they have the same signs. So speeding up for t greater than 1 second. And I guess we could include the endpoint there because it's not the edge of concavity, it's the edge of velocity. And then slowing down for 0 to 1. And we would include it for 0. We could include it for 1. And then we wouldn't include negative infinity to 0 because we only want positive time. So that's speeding up, slowing down. And then total distance, I just showed you guys the trick. We'll explain it more in detail later. You can put your endpoints on here, 0 to 5, any critical points, turning points there. Plug 0 in, you get 2. Plug 1 in, you get negative 1. Plug 5 in, you get 25, 120, 625 minus 20 plus 2, so it's 607. And then distance is the absolute value of the difference between each of these positions. So this is 3 and this is 608. And so the total distance is 611 if you add these up. 611 feet. 611 feet. Okay. Next problem was 19. 19 says 7022 position function particle moving along the coordinate line is given. So they're giving you the position function. And then it says using the method of example 6 to analyze the motion particle for t greater than or equal to 0 and give a schematic picture of the motion as in figure 5.4.6. So go back, look at those in the book. Essentially, we're going to try and draw a picture of something that we were kind of looking at, kind of picture like in the notes. So we probably want to find each of the equations, 3t squared minus 18t plus 24. Acceleration equals 6t minus 18. Then we probably want to figure out where these equal 0. So this one will be, we could factor a t out. That's going to be t squared minus 9t plus 24 equals 0. See if we can factor this more. Positive and negative. It's got a two negatives that multiply together to get negative 24. So 4 and 6. No. Wait, did I make a mistake here? Oh. Yeah, maybe we don't need that. And then we can set this equals 0. We'll come back to that if we need it. Velocity equals 0 is definitely going to be important. So we factor this one, take a 3 out, and factor this t minus 2t minus 4. So these are turning points when position is 0. We could probably do acceleration equals 0 and do a line check for speeding up, slowing down. So I'm really just trying to find all the information about this, and then we're going to make a picture. So one of the things we could do, we could just make a table and plug in a bunch of times into this, like 0, 1, 2, 3, 4, 5. Plug in a position equation. You plug 0 in, you get 0. You plug 1 in, you get negative 8, 16. You plug 2 in, you get 8, minus 8 minus 36 plus 48. So that's going to be 56. That's going to be 20. Plug 3 in, you're going to get 27 minus 81 plus 72. So that's going to be negative 9. That's going to be 18. Plug 4 in, you're going to get 64 minus 30. 9 times 16, 90. 144 plus 98. So let's see, that's going to be negative 80. That's going to be 8. Made a mistake here somewhere. This would be 96. Okay, so that's going to be 16. Maybe that's enough. Now I'm going to do a quick. So this is when the graph has stopped. And I'm going to do a quick speeding up, slowing down, check. 2 line checks. So velocity, it's going to be 2, 4. Acceleration, put it 3. Test, t equals 5 here. It's going to be positive, negative, positive. Test, t equals 4. Acceleration is going to be positive, negative. So here it is speeding up. Here it is slowing down. Here it is speeding up. Here it is slowing down. So that could all help. So now we're going to draw a picture. The number line. And we're going to say, okay, we're going to start at 0. This is the position of the number line. So it's starting here at t equals 0. And then it's going to move to the right until time 2 when it's at position 16. So it's going to move to the right until time equals 1, and it's at 16. And the whole time it's actually slowing down. Slowing down. And then it's going to slow down to a stop at 2. So we'll put that here. And at that point, it's only at 18. It's at 20. So this is time equals 2, and it has stopped. Then it's going to change direction. So now it's actually moving to the left from 2 to 4. So it's going to keep moving left. It's going to be at 18 here at time equals 3. And from 2 to 3, it's speeding up. So it's speeding up in that little chunk. And then it's going to get to time 4 at 16. And that's where it stopped again. So it's speeding up. Now from 3 to 4, it's actually slowing down again. Slowing down. Now it's going to start to move to the right again. And it keeps moving to the right after that forever. And here it is speeding up. So that's kind of the picture we're going for. Kind of illustrate what's going on here. Problem 26. Actually do problem 26 as part of the next lesson. So if you have questions about 26, we will cover it as an example in the next lesson because it involves gravity. And we haven't really talked about gravity yet, but we're going to talk about gravity in the next lesson and start to apply these ideas to that kind of scenario. All right.